Hello, everyone. I'm Arthur O'Dwyer. I'm going to be talking today about SFINAE, about just a soupçon of the SFINAE, a small quantity of it. When I submitted this talk, I think the most concrete piece of feedback I got on it was like, SFINAE, that's awesome. Can you change the title? People aren't going to know what that means. Not the SFINAE part, the other part, the French part, yeah. But yeah, I kept it. So here's what we're going to be talking about today. Basically, the first half of the talk, I'm going to introduce the general concepts that we're talking about, introduce SFINAE, and talk about the three kinds of spaces that I had on that opening slide. Or nope, not that opening slide. Sorry, this next slide. And then in the second case, in the second part, I'm going to talk about some particular case studies and give you some anecdotes. So let's talk about template metaprogramming. Let's talk about writing our own type traits. And a way that I think about this is that there are sort of three spaces in C++ that are all sort of orthogonal to each other, or we can map from one to the other. We have value space, the space of values like 42 and true and false and hello world. And then we have type space, the space of int and bool and std string, and true type and false type, which we're going to talk about. And then there's also this sort of SFINAE space, which I'm not sure really has a name. I'm going to call it SFINAE space in this talk, where things can be well-formed or ill-formed. And that's the salient thing about things and entities in this space, is are they well-formed C++ or ill-formed in a way that makes them not exist? Do they exist or not? Let me show you an example. Here's an example of a couple of utility classes that are in type traits that we're going to be using a lot in this talk, and I'm going to put them on this slide just so you see how they're implemented, because they're going to come up over and over, and if we don't understand these, we're not going to understand anything else. Struct integral constant. It's a class template. It has two parameters. It's got a type parameter that says what is the type of this constant, and it's got a value of that type, which I'm calling v here. And it's got a member value that expands to v, and some other members that don't matter. And particularly, we can make an alias for that. Bool constant is just an integral constant of some bool value, and in particular, we have two of those that are particularly interesting because there are only two values of type bool, true and false. So I can make a bool constant, which, remember, is just, now this is a specific class. It's a particular class belonging to this class template, whose value is true, and one whose value is false. And I'm going to call those true type and false type. And so what I've done here is basically take the values from value space, true and false, and raise them into type space. I now have two types, true type and false type, that in some sense correspond to true and false. But there's nothing special about these, other than they got into the standard library. I could write this entire code again and just change all the identifiers, change integral constant 2, and bool constant 2, and true type 2, and false type 2, and that would have the same claim, the same dibs on representing what is really the correct type mapping of true and false. So there's nothing magic about true type and false type, other than that we have by convention decided that std true type and std false type are the things we're going to use when we want to take the values true and false and raise them from Boolean values into types. And so I'm going to use a lot of these when I define type traits like this. Here, we're not using SFINAE yet. No SFINAE yet. Partial specialization, though. I have here a type trait, which I'm going to call isReference v, and I'm going to make this an inline context for bool. It just expands the value of some isReference type trait. The isReference here is the old school C++ 03 type traits. Each type trait is a class template, and we have a base template here. So for any t where it's not partially or totally specialized, isReference of t is going to be inheriting from false type, which means it's going to have a member named value, which inherited from false type, and that value is going to be false. And I'm going to make two partial specializations, one for tref, one for trefref, and both of those I'm going to say are true type. So now when I ask the compiler, I say I would like to know what is isReference v of intref. It goes and says, well, that's going to be isReference of intref, : value, and intref, and it's going to do a little bit of pattern matching on intref, and it's going to see which of these is the best match for it. Is it tref? Is it, if I have intref, does that look like a tref for some t? Yeah, t could be int, okay. Is it tref? Well, t could actually in that case be intref, but we're not going to deduce that. There's a better match with tref. And if there were no match that made sense, we would just fall back to the base template. In this case, we don't fall back to the base template. The partial specialization for tref looks great, so this is true. In this case, int doesn't look like tref, and int doesn't look like tref, so we fall back to the base template and we get false type. All right. And we don't have to just have things that are Boolean-ish that return true and false. We can return other types as well. So here's remove reference. Looks exactly the same as the last slide, except that we've changed it from having from being either true type or false type to having a member type def named type, which is either the removal of the reference qualifiers from t or t itself. So again, intref looks like tref, so type will be t, which is deduced to be int. Or if we give it just plain old int, it doesn't look like either of the partial specializations. We'll take the base template. So the compiler is looking to see which partial specialization looks like a good match, and if it doesn't find one, it will use the base template. Now, what happens if we try the opposite operation? So not removing the reference, but adding reference. Here we have add L-value reference. You could make an add R-value reference as well. Here, it seems like we don't really need partial specializations. All we do is we take the t that the user gave us, and we add a single ampersand to it, and it all works great. And some people in the audience might be thinking, well, this doesn't really look great, and that's because you don't know reference collapsing, so go watch my talk from last year. Reference collapsing is not a problem, but there is a problem. And the problem with this is void. I put void in here, and I say I would like to know what do I get when I add an L-value reference to the type void. And that should be void ref, but that doesn't exist. So that is ill-formed. And that means the compiler gives us a hard error, and our program doesn't compile. So if we want this type trait, this add L-value reference t of void to be well-formed, we have to do something special. Does that make sense that we can't make a void ref? We make a void star, but not a void ref. Okay, that's like the only type where you can't do that. Every other type, I think, you can make a ref, but not void. So if you ever want to know if something is void, now you know how to do it. All right, so we could do something like this. We can use partial specializations here. We can say add L-value reference has a base template that just adds a ref, but then we're going to partially specialize it. So if someone gives us something that looks like void, maybe with some CV qualifiers on it, we'll pick up the partial specialization, and we'll just say, well, when you try to add an L-value reference to void, you get void. When you try to add it to const void, you get const void, and so on. This actually works, but it is pretty tedious, and it's not really future-proof. It's kind of weird that void is the only type where you can't make a ref to it already, and maybe 3 years from now there will be another type like that. Unlikely, but it could happen. The rules sometimes change. And what we really want is something where we can ask the compiler. The compiler knows, right? Because it gave us the error in the first place. It said you couldn't do this. So it knows whether it's OK to put a ref on a type or not. Can we just ask it somehow? Would this be well-formed? Can we ask questions about SFINAE space, about well-formed versus ill-formed? Turns out we can. Let's do this. There's a bit of code on this slide. So here I have a base template called ALR-impl. And it takes now 2 template parameters. And if you're reading ahead, yes, this is more complicated than it needs to be. T and something I'm going to call enable. And I'm going to partially specialize it for the case where T is deduced and enable is remove reference T of tref. So when this pattern is the best match for the things that the user actually gave us, we're going to use the partial specialization there. So now let's see what happens when we say add L-value reference of int. Add L-value reference of int is going to be ALR-impl of int, comma, remove reference T of int. Well, this is just int. So we have ALR impl of int comma int, and that is ALR impl of int comma remove reference t of intref. Yeah, remove reference t of intref is actually int. That checks out. The partial specialization is a match. We always prefer to use a partial specialization over the base template if we can. So we'll deduce t as int, and we'll have type be intref, which is what we wanted. It added a ref. Skipping down to the last one, though, add L value reference of void. Here, remove reference t of void is just void. That's not a problem. So we have void and void. And here, we look at the partial specialization again, and we have ALR impl of void, comma, remove reference t of void ref. Now, is this partial specialization a good match for void and void? Well, void is a great match for void on the first parameter. But on the second parameter, we're trying to match void to this thing that's spelled remove reference t of void ref. And that's ill-formed. That's not even a thing. So no, that's not a good match. If it's not even a thing, it's not a good match. So no, don't use the partial specialization. We fall back to the base template, and we have using type equals t, using type equals void. So it does the right thing. So yeah, here this enable is indicating that the thing that would go there, it wasn't even ill-formed. We'll fall back to using the base template. All right, but this is really complicated. We're implementing add reference in terms of remove reference. We can actually do a little bit better. What does it say? When we want to use the specialization, the bolded expressions in the partial specialization and in the point of use in the call site have to evaluate to the same type. So the remove reference t of t and the remove reference t of t ref have to come out to be the same thing. Then we'll use the partial specialization. If they don't come out to be the same thing, we use the base template. All right, but can we devise a simpler pair of type expressions? The type expression in the partial specialization has to be ill-formed exactly when tref is ill-formed. Otherwise, it has to match the concrete type used at the point of use exactly. And so we had a problem there that figuring out this pair of types where one of them has to be ill-formed exactly when the other one is, and otherwise they have to match exactly, was complicated. We would like a simpler type expression for this. And we can get it. We use void t. So up at the top of this slide, this is new in 17. But you can write it yourself, and it looks just like this. There is no code omitted here. Those are literal ... Void t is just a class template that takes any number of types, and it is void. It's an alias for void. So now what I've got here is add L value reference is ALR impl of t comma void. So now I've taken my remove reference t of t and I've replaced it with just void. So this is well formed. Up here in my partial specialization, I've got void t of tref. Now this involves tref, so it's not going to be well formed if tref is not well formed. So if t is void, this partial specialization is basically going to disappear. It's not going to participate. It's not going to be a good match because it's going to be ill-formed. And I have my base template the same as always. I'm going to go on through this. Well, once I have this, void t is now a tool for really stamping out these, just mass-producing these type traits. Right? It becomes very easy to write a type trait without having to really think about, without having to think too much about the particular gymnastics that you have to do to make something ill-formed. I can just say, for example, here's add L value reference, which we saw before, and it has that same form of t comma void, and up here in the partial specialization I have void t of tref, because that's the thing I'm interested in the well-formedness of. So I sort of test it right there, and then I use it. And otherwise I'm going to fall back to t. I can add R value reference. That looks exactly the same. I just say tref ref in 2 places. I can say add pointer. That looks exactly the same, except I say t star in 2 places. So this is easy for really stamping out, mass-producing these type traits with very little code. But what if the thing that we want to know if it's ill-formed, we want to do something based on the ill-formed or well-formedness of it, what if that thing is not a a type expression, like tref or t star? What if it's a value space expression, like a equals b, or the ability to construct something or static cast something? So we add another function. We add declval. Declval is a function whose declaration exists, but whose definition doesn't because we don't need it. We're only ever going to call it in the context of something like decltype, where we're not going to actually evaluate it. We're not going to need to know its body. We just need to know what does it return. And what it returns is something of type T. And we use it like this. Here I have a type alias, a template type alias for the result of an assignment of something of type U to something of type T. I'm going to say, let's suppose that I had something of type U, and let me just suppose I had something of type T, and let me do the assignment from U to T. And that let me just suppose part is what declval is doing. It means that I don't actually have to say how I would get something of type T. I don't have to say, well, what if I did T with like curly braces, because T might not be default constructible. I'm leaving out the details of where that T comes from. I'm just saying, let's suppose I had a thing called declval that gave me a T. Now, I don't have to worry about that. I just care about this assignment expression. What is the type of that assignment expression? And in this case, we see that it tells me the right answer when there is an answer. But when the assignment would be ill-formed, such as trying to assign an int star into an int, then I have a problem. I've said, I want the decl type of this thing, but that's ill-formed, so I get a compiler error. So I can use SFINAE again. I can use a thing called expression SFINAE. I've heard that Visual Studio has historically had trouble with this thing, but I've tested this code. Even MSVC is happy with this code we've got here. We've got a type trait. It's called isAssignable. It's gonna return either true type or false type. And I'm going to do the same thing where I have a point of use for this isAssignable impl, and I have the base template and the partial specialization. And the base template just says, by default, I'm going to say, no, it's not assignable. And in the partial specialization, I'm going to have a template parameter, and that template parameter is going to come out to void. But it's going to come out to void in a way that depends on the well-formedness of declval T equals declval U, of the assignment that I'm interested in the well-formedness of. And in that case, if this partial specialization is well-formed, it will definitely come out to TU void, which is what I put in, and so it will be a very good match, and so it will get selected and will get true. And if it's not well-formed, then we'll have no choice but to use the base template and we'll get false. So again, I've taken the well-formedness, ill-formedness of this expression, and I've managed to sort of project it into value space. Well, really into type space here, where I'm getting out true type or false type, and I can take that and project it into value space and get true or false. So I'm taking the well-formedness or ill-formedness and projecting it into a space I can work with without having to worry about getting compiler errors, just about testing Booleans. Now I used the little weird expression here where I just took the expression and cast it to void and took the decl type of that. There has to be a decl type in there somewhere because we've got an expression and we want to get a type. But yeah, I could use any of these formulations. Here they are at the bottom with the expression factored out. And they're all about the same length. And I've been tending to use the shorter one. All right. So now we have this decl type, we have the idea of expression SFINAE, and we can start mass producing things. We can mass produce, here's is static castable. I wish this were in the standard. I always write it. Is static castable just says, can I static cast from T to U? And I can stamp that out. I could stamp out is polymorphic. A type is polymorphic if and only if dynamic cast works on it. So that's how you tell if something's polymorphic. You just try to dynamic cast it. But you do it in a way where when it fails, you don't get a compiler error. You just get false type. You get the base template. Let's see. And in this case, you'll notice I've actually I'm using void star and void star because I already know it's going to. I'm casting it to void star. I don't need to further than cast it to void. Here's is constructible. Can I construct a T from a bunch of U's? That's a variadic. There are variadic params there. U's is a pack of types. Not a problem. Works great. Is no-throw constructible? Exactly the same as the last slide. Its SFINAE is under the same conditions. The partial specialization becomes ill-formed, and I fall back to the base template under the same condition. But even when we select the partial specialization here, I then actually want it to sometimes be true and sometimes be false. So the stuff on the right-hand side of the colon here is now coming out to true type or false type based on the no acceptness of this expression. So that's no problem either. All right. New topic. Conditional T. Conditional T is like the ternary operator for type expressions, like the question mark. It takes two types, T and F, and it produces one or the other of them based on a Boolean condition. Now, just like the ternary operator, if you put in something ill-formed, the whole thing becomes ill-formed, right? You can't compile it unless you know what all the pieces mean. If one of them is ill-formed, the whole thing's ill-formed. So now what if we just simplify this a little bit, and we just cross out the type F there, we simplify this down. We get something called enable if T. This looks very similar. We go back to here. We're just taking out class F through all of this. We keep the bool, we keep the T, we just kill the F. And that means we also kill the type alias for type in the false case. Then we end up with this. Enable if T takes a well-formed type T, which defaults to void, but never mind that, and produces either T or something ill-formed, depending on its Boolean argument. Produces either T, which is well-formed, by definition, I hope it's well-formed, or produces something ill-formed, something that doesn't exist. So this is actually a way of going back the other direction. We saw partial specialization as a way to go from something which might or might not be ill-formed to a Boolean. Now we're taking a Boolean B and we're going backward to say if the bool is true, I want this expression to be well-formed. If it's false, I want this expression to be ill-formed, this type expression to be ill-formed. And I like to have this little convenience type def here, bool if T, where the default enable if T is more like void if T, but I find it useful to be able to get values of this type. Somehow, sometimes we'll see that when we get to the anecdotes. All right. So as I just alluded to, now we've gone in both directions. If we have a Boolean that we know is well-formed, it's either true or false, and we want to map it into the SFINAE space of well-formed or ill-formed, then we say enable if T B, and that will be either void or ill-formed. If we have a value expression that might be ill-formed, and we want to project its well-formedness into a Boolean, true or false, then we go the other way. The first step is we make sure that we have either void or ill-formed, okay? And then we use a partial specialization here to turn that back into true and false. And we can just go back and forth if we want to. So now we know how to go both directions, from value space to type space, to SFINAE space, to type space, to value space. I went through that real fast. Are there any questions about this part? Awesome. Let me catch up to my notes here. All right. Let's talk about some case studies, some anecdotes, some things I have found to work or not work, and what I did about them. So here's case study number 1. SFINAE away a function that is not currently a template. So here's my motivation. Here's my motivation for this. So in C++17, there's a new header called memory resource, and in it, it has a couple of things in the std_PMR namespace. I assume by this point at CppCon, you've all seen at least one talk on allocators. And if you haven't, I don't know where you've been all this time. So std_PMR has this class called memory resource. It's a classically polymorphic interface to an allocator or to a heap. And there's this function getDefaultResource that gets you the global heap, which is terrible, by the way. Global variables suck. Don't use them. And there's this template class, polymorphic allocator, and it has a pointer to a memory resource, and it has a default constructor that gets the default resource. Okay. Who knows what this is?
Dog dressed like a woman.
Dog dressed like a woman. This is a fancy pointer. And I'm not the first one at this conference to use that joke. I was highly disappointed and I was beaten to it. All right, so let's fancy pointer all the things. So what a fancy pointer is it's a pointer-like type, behaves like a pointer. You can star it, you can plus it, but it's not a native pointer. So, and C++11 allocators are allowed to have pointer types that are fancy pointers. The PMR allocators are not, but we can add it. It's easy. Let's just do it. So here I have a fancy memory resource, and it's templated on its void pointer type. It might be void star, it might be something else. I have a fancy polymorphic allocator, templated on T. It allocates T's, and it also has the same void pointer as the fancy memory resource contained by it. And I can make type defs then for polymorphic allocator and for memory resource. But now I also can make type defs for a shared memory resource and shared memory allocator coming from boost interprocess offset footer. And never mind what that is, doesn't matter. But now we have a little bit of trouble. Now in our fancy polymorphic allocator, which is now templated on the fancy pointer type, we now have a pointer to a fancy memory resource, but our default constructor is still trying to initialize that pointer from getDefaultResource, which is this global function that returns a memory resource star. And that works great as long as you don't use fancy pointers, like much of the STL. But in this case, if you try to instantiate it, if you try to instantiate the SHMEM allocator we saw on the last slide that tries to use boost offset putters, you have a problem. You can't convert getDefaultResource, this fancy memory resource, which is a plain memory resource, to a pointer to a fancy memory resource, which is okay. I'm actually happy about this because I don't like that global variable and I do actually want it to go away. I'm totally happy to say the user of this, if they want fancy pointers, then their allocators will not be default constructible. That's okay. You don't want to default construct a polymorphic allocator. It doesn't make sense. So I want this constructor, this default constructor, to just go away. I don't want to see it unless that expression would be well-formed. And there are some usual tricks, which I'm not even going to talk about here, such as you can put the SFINAE on the return type of the function, but you don't have a return type in this case. You can make it an argument type, but this is a default constructor. There's no argument types to put it on. You can make it a template parameter, but this isn't a template. So what do? Well, we can just make it a template. So we make it a template. So here I have my same default constructor, only now it's a function template. And it takes one argument, and that argument is going to default to enable if t if void pointer is the same as the native void pointer. Then I would like this to be enabled, and otherwise I would like that default argument to be ill-formed, in which case you will not be able to call this function, because there's no way to give it a non-default argument. It's a constructor. And so I want it to be ill-formed. So I try this. I try compiling it, and it doesn't work. And Clang gives me a very helpful error message that says, I see you tried to use enable if. Enable if cannot be used to disable this declaration. It doesn't tell me really what to do about it. It just says, I see what you're trying to do, and I'm not letting you. All right. Let me catch up to my notes again. So what's going on here? Why is it telling me that it can't do what I asked? Well, turns out it doesn't work because there's nothing in the enable if t, which you can see sort of under the big X here, that depends on the point of use. And the compiler, when it's trying to figure things out, will generally be as eager as possible. So things like template default arguments, the compiler will try to resolve that if it can at the point of the declaration. and it won't wait until the point of use unless there's some reason it needs to. Like if that expression, enable if t is same v void putter void star, if that depended on an argument to another template argument, for example, then it would have to wait, obviously, until it knew that argument. But in this case, it knows what void pointer is at the time that it starts instantiating the whole class body. It says, oh, void putter, that's boosted process offset putter of void, and so it is not the same as void star, and so you want the default to be enable if t of false. Oh, that doesn't exist, and it throws an error. But we can do a mechanical transformation to kind of trick the compiler a little bit. And this is the first trick here. We make a bool. We just add another template parameter, bool b, and we initialize it to that whole condition. And then we just have our same little class at the end there, class equals enable if tb. And this tricks the compiler. The compiler can now do all of the same evaluation it was doing before. It can figure out that this bool b defaults to false. And then it can figure out that this class, in that case, would default to enable if t of false if you pass the default for both arguments. But the compiler doesn't know C++ as well as you or I. It doesn't know that you can't pass non-default template arguments to a constructor. So when it says bool b defaults to false, but the user might pass true. They can't, but it doesn't know that. So it can't actually evaluate enable if tb until the point of use, at which point it will find out whether the user is actually using the default false for b or whether the user has figured out how to shoehorn a true in there, which, again, they can't do. And even if they could, we're not really concerned with users misusing our library. So there we go. That was the trick. And it works. So now we can instantiate our fancy polymorphic allocator. It no longer throws a hard error when we do that. And it does throw a fairly nice error when we try to default construct one of these things, which we have now made no longer default constructible. I say fairly nice. It's not really. The error message from Clang says requirement false was not satisfied. But we can actually make it nicer. So we can start with, this is what we had before, that was too eager, it was evaluated eagerly, it was ill-formed, and we got a hard error when we tried to make that declaration. Here's the trick I just showed, where we pull out this entire condition. We take the condition out, we put it, name it b, we enable if tb. That gives us requirement false was not satisfied, which is true, but not helpful. Another thing we could do is we could leave the condition as it is and just AND it with bool b, which defaults to true. Again, the compiler has to wait until the point of use to find out whether the user might have somehow managed to pass in false for b. So this also works. Or probably the best trick that I'm aware of is make one dummy parameter of just one of the template type parameters you're going to be using. In this case, I say void pointer. That's the only one I am using. But if I had like tuv, I would only have to copy one of them. Name it the same thing with a little underscore and use the underscore one down here. This gives me a fairly nice error message. Of course, in this case, I'm using boost in the process offset pointer, so the error is like crazy long. But it's actually telling me what the thing is that wasn't satisfied there. Yeah.
Would a template deduction guide alter the dependency on the point of use at all?
Would a template deduction guide alter anything about what's going on here? I have no idea.
The fact that you can trick the compiler, is that because the compiler is not yet sufficiently smart, or is that written into the rules?
It is certainly written into the rules of the language yes, this trick works. It's not like a missed optimization. I think it's a little quirk of the language that even though there's no way to express the passing of non-default template arguments to a constructor, the compiler is still required to act as if there were some such way.
But there is, not for new construction, but you can actually call a constructor directly.
when you call the constructor directly. I mean, you can use placement new, but I think that's the same problem. And otherwise, no, you can't get a constructor is not a function or anything. You can't get a function pointer to it. Anyway, I'm going to go on because we have the moral of the story is if you're running into a problem where something is happening too eagerly, split it up. Add a level of indirection that solves all problems. Pull out just a bit of it. And by doing that, you can get the compiler to sort of wait until the point of use. Case study 2, conditional explicit. Here's the motivation. We're sticking with fancy pointers. I was looking into fancy pointers a lot lately. So here's a fancy pointer. This is now boost offset putter. It has a bunch of stuff I'm not showing here. This is also completely irrelevant how these things are implemented. But the interesting thing is that what I want is just like a regular T star, I would like to have a conversion from T star to U star, or in this case, offset putter of T to offset putter of U. I'd like to have that conversion exist whenever those pointers would be convertible. But I don't just want to have implicit conversions between all possible kinds of offset putters, because that would let you cast away const, it would let you do all sorts of stuff implicitly, and I don't want that. So I would like to have something which is always available, but sometimes you have to explicitly say it, right? Sometimes it's an explicit constructor, and sometimes it's non-explicit. And another place this comes up, by the way, is also in optional and probably tuple and some other utility types like that have conditionally explicit constructors. So let's see. So our first attempt. Here's our first attempt. I have offset putter, and I have a non-explicit constructor if U star is implicitly convertible to T star, and I have an explicit constructor if U star is convertible to T star with a static cast. And we try to compile this, and it doesn't work because we just put the constraint in a comment. That's not going to work. We actually have to write code. Constructor cannot be redeclared. Okay, so it's treating these as the same constructor. Just one of them has explicit and the other one doesn't, but it's saying you're trying to redeclare the constructor. Not only that, you're trying to redeclare it with a slightly different signature, which is certainly not going to work. All right, so let's put in code. We do the same thing that we did before. Right? We've now figured out that if we want to constrain a constructor, we just make it a template. Now here it already was a template, and in fact, the condition, the enable if condition that we're trying to use here is dependent on U, which is not known until the point of use, so we're following all the rules. And we try to compile this, and the error message has not changed. All right. So the answer here is that the SFINAE that we've been using here is only in the default template type argument, the default argument to template type parameter, right? So if we forget about the value of the default argument for the moment, our signatures still look very much the same. We've got a constructor, which is a template that takes two template type parameters, one named U and one unnamed, and it has some default, but we don't care about that right now. And then it has these arguments, const offset putter uref, and then the other one looks exactly the same. It takes two template parameters. We don't care about what the default is. So we give the second class parameter a new default value in the second declaration. But that's just a violation of the one definition rule. That's not actually a change in the signature of the fundamental entity-ness of this template. What we want here is to have not just a repetition of the declaration, we actually need to have two different templates. And so we need to make sure that they are really two separate entities somehow. One way we could do that is we could just add a dummy parameter. Right? Now they have different parameter lists. One of them takes an offset putter ref and an int, the other one takes an offset putter ref and a double. They're now different, and it's totally fine to do this. This works, but it's not a great idea. At least I don't like it. Philosophically, it doesn't seem right. Because we have to invent this new ad hoc tag type for each mutually exclusive overload, and also because it involves default function arguments, which are awful. Please don't use them. So we can do better. A better but subtler solution is to change not the function argument list, or function parameter list, but the template parameter list. we need to make it so that these template parameter lists are somehow different. They can't just be like class and class. They have to be different somehow. And this is where I bring in my bool if t. So here, this first one has the class u as usual, and then it has a parameter of this type. Now this type depends on u, so it's not going to be known until point of use, so it can't be evaluated eagerly. We don't have to worry about that. But at the point of use, the compiler is going to be trying to make up the overload set, figure out which constructors are relevant to this use. And it's going to say, okay, I know u star and t star at this point, so if they're convertible, let's say that they are not convertible at all. In that case, is convertible v of u star t star will be false, and bool if t of false is ill-formed. So here we have a constructor template which takes one type parameter and one non-type parameter of, oh yeah, that type is ill-formed. Never mind, that's not going to be a good match. Right? If it's ill-formed, it's definitely not a good match. And so it will just ignore this one. If it is convertible, this one will be fine, and it will take a template type parameter, class u, and it will take a bool argument, right? Because bool if t of true is bool, and the bool will be true. Will default to true, not that that matters. And in this case, if it is static castable but not convertible, then this one will take a bool, and the other one will be ill-formed. And so this ends up working. At the point of use, the compiler computes the overload set, which evaluates bool if t of each of these expressions. These expressions are mutually exclusive, which is important. They'll never both be true at the same time, and we can tell that because one says is convertible and the other one says not is convertible. So they're mutually exclusive, and so only at most one of them can be true, and so we don't have an ambiguity anymore. So to kick an overload after overload set, we need to not only have something ill-formed somewhere in there, but it has to be somewhere in there that's going to affect the fundamental name of that entity, its signature somehow. It's not enough to put in a default argument or somewhere else that is not contributing in some way to, I think of it as the name mangling. I had a slide in here saying, think about name mangling, and then I thought, that's just even more confusing. Don't think about name mangling. All right, problematic parameter types. Who can guess what the motivation for this example is going to be? It's fancy pointers. Fancy pointers have this thing called pointer traits. It's in the library. And actually, in this case, I'm interested less in the fancy pointer one as just the pointer traits for regular old native pointers. We have a base template, and it has some stuff in it, but we don't care. The base template, let's just assume that it exists. But there's a partial specialization for regular pointers, T star. And pointer traits, you can tell by the name, is a traits class. It's a place where the library can sort of hang a bunch of traits, relevant details about a class, without having to reopen that class and stick them in there because you might not always have access to that class, or that class might not exist. In this case, T star is not a class. It's a primitive type. And so if we wanted to ask T star, hey, what is your element type? We can't ask a member type def of T star. It doesn't have member type defs. It's a pointer type. But we can ask pointer traits of T star, : element type, and it will tell us, oh, the element type is T. So there's this partial specialization in the library, and it has the pointer type itself. It has the type of the thing pointed to. It has what you get when you subtract two of them. It has, this is cool, the ability to rebind a pointer type to say, I have this kind of pointer, but to a different type. That's a alias template there. And then it also has this other function that's new in 17, I think, called pointer to. Pointer to takes the actual native address of an object and gives you back a pointer of this type to that object. And it just returns, in this case, it just returns the address of R. But if we were trying to get, let's say, a boost interprocess offset putter to a certain object, that would involve constructing an offset putter somehow. So in this case, I'm only interested in this. Does anyone see the problem with this yet? The problem's on this slide. I've seen it before. Tref. Tref, yes, the problem is void, always. Always the problem is void ref. So a pointer trait's a void star. If I try to instantiate that class, it turns out I cannot instantiate. I get a hard compiler error when it gets down to trying to make the static member function pointer2, because pointer2 wants to take a parameter of type void ref. All right. Right, cannot form a reference to void. All right, what do we do? Well, we follow our recipe. We're going to SFINAE away non-template function. This is a non-template function. So step 1 is make it a template. Step 2 is we want to SFINAE it away when is void v of t, or sorry, when not is void v of t. We want SFINAE away when t is void. We want it to exist. We want it to be enabled when t is not void. But we know that t is known already at the point of the declaration. We need to trick the compiler into waiting until the point of use. So we add our level of indirection. We make this bool b. You know, we've now followed all of the guidelines we've learned. We've done this great. And the compiler error message doesn't change. It still says cannot form a reference to void. So it doesn't work because the function's signature is also being eagerly evaluated. Let's go back here. So this tref right here is being eagerly evaluated. So regardless of all the stuff in the template that cannot be eagerly evaluated, this can be, and it evaluates to void ref, which is ill-formed. So we got a hard compiler error. All right, so let's try this. We're going to say, OK, well, here's the first thing that jumps to mind. At this point, we're just banging on the keyboard, right? So I'm going to add another parameter, class tr, and I'm going to say, look, if I'm going to take a parameter now of type tr. So, haha, I've now made it so you can't deduce that until point of use, because that depends on b, which depends on the default argument. So, OK. And it's only going to be tref if not b. I try this. And I get the exact same error. Exact same error. This error is not changing. It's not being more helpful. It's not being less helpful, but it's not changing. Can't form a reference to void. And that's because right here, I have tref. The compiler can see this. It knows what t is. T is void. Tref is void ref. That's ill-formed. And it throws an error. Right? This is the same thing that would happen with conditional t. And conditional t takes the bool and the type t and type f, and they both need to be well-formed. And if one of them is ill-formed, then the whole thing is ill-formed. Similarly with enable if t. It takes a bool and a single t, and if that t is ill-formed, the whole thing is ill-formed. So the whole thing here is ill-formed. Still not working. All right, here's what we're going to do. We're going to take that tref, and we're going to add a layer of indirection. I'm going to split it up. Haha. There we go. Suck it, compiler. Got enable if t not be of t. And now you don't know what that type is, compiler. You don't know enable if t of some stuff. You can't compute that. But whatever that is, I'm going to take a ref to it. So now you definitely can't evaluate that until the point of use. And we do this, and finally the compiler is happy, and it compiles. When we run our code, it segfaults. We lost track of what we were actually doing other than getting the thing to compile. Now when we have pointer traits of a non-void pointer type, and we try to call pointer2 on the address of a variable like x, we get a segfault. We've forgotten to pay attention to the meaning of the syntax we're using. We provided this default, enable if t of not b, comma t ref for tr, but template defaults are only used if we can't deduce that argument from the parameter list, which in this case we certainly can right here. If we pass in a x, let's say x is an int, what's tr going to be? It's going to be an int. And we're going to return the address of that int, which is an argument, yeah, it's in the parameter slot, and it's going to be gone. We're returning a dangling pointer. We're certainly not returning pointer to the original x. Right? This tr is going to deduce to int. We wanted it to be int ref. It would have been int ref if we used the default, but it was deduced, so it's int. So what we need is not really this new template parameter, although we could make that work actually, but we need not a new template parameter. We need a new constraint on the existing function parameter so that the existing function parameter can match either tref or ill-formed. So we could do something like this. So here, again, enable if t of not b comma t is something that cannot be eagerly evaluated until we know what b is, and we're not going to know what b is until our point of use. And then we're going to take the ref of that. And now this whole thing, this is a concrete type, right? It depends on b and t. It doesn't depend on anything the user is passing into us. So it's not going to be deduced. It's going to evaluate to something like int ref, or it's going to evaluate to nothing at all. It's going to evaluate to void ref, which is ill-formed, and so you're not going to be able to call pointer to. And this works, and it has the right behavior. And when t is not void, the call side of pointer to x sees that b was not provided, so it uses b equals false, because t is not void. And enable if t of not false comma t is just t, so t ref r. You get the right thing. When t is void, then number one, there are no call sites, because no one can ever pass in a reference to void, and we're actually done, as long as this doesn't cause problems, which it doesn't. So lesson 3 is don't lose sight of the meaning of your code when you're trying to get it to compile. In this slide, you still need the default template parameter. Yes, you do still need it, because if you got rid of bool b and you moved is void vt down into here, then this whole expression would depend only on t, which we know. And when t is void, this will be ill-formed. We'd be back where we were.
Plus, it wouldn't be a template function.
At that point, it wouldn't be a template function, which would be fine. We actually don't want it to be a template function, but if we want it to SFINAE away, we have to make it a template.
Right, yeah. It's not a template.
Right.
With the slight change of semantics, could you just make it a regular template function that uses t, and then SFINAE away u is the void? Now it's not exactly the same semantics, because now you have a pointer to the u ref, but you could also SFINAE away if u is not the same as t.
I strongly suspect you could make it even simpler than this, actually. I think you could just say template class u equals t, pointer to u ref of r. And that probably does the same thing. But one more question.
Please repeat his question in the platform.
Oh, his question was, can you rewrite this in some way? And my answer was, I'm not going to think about that, but yes, you can rewrite it differently. Yeah. So even as you're trying to do all of these SFINAE tricks just to get the thing to compile, remember to go back after it compiles and actually look at the code and see whether it does the thing that you expected it to do in the first place. Sometimes you get a seg fault, and then it's nice that the computer reminds you to go back and look at your work. But even when it doesn't seg fault, you should still do that. All right. Does anyone know what this is? This is 4 pugs in aviator goggles and top hats, and they're smoking cigarettes. Yeah. I didn't actually think we'd have time for this, but we have 10 more minutes, so I'm going to try to get through this. Ton of stuff promised in the abstract, didn't make it in. Let's suppose, so in our second test case, we saw that we need the conditionally explicit thing, where we had 2 mutually exclusive cases, right? Either it was convertible or it wasn't convertible. We wanted to do one thing or the other, but never both. What if our dispatch cases are not mutually exclusive? So here's an example from the STL. No more fancy pointers at the moment. We've got here distance, std distance, right? It takes 2 iterators and tells you last minus first. But you can only actually express last minus first if they're random access iterators. Luckily, we have this thing called iterator category. And so we can say tag dispatch on iterator category, we go to random access iterator tag, or if it's not a random access iterator tag, at least it will be an input iterator tag. Technically, maybe we need one for output iterator too, I'm not sure. Go see last year's talk. But the idea is that we have one overload. These are no longer partial specializations. They're separate function overloads. They have different argument types. But one of them takes a very, very derived class, random access iterator tag, and the other one takes a base class. And so statically, overload resolution will prefer, if it can see that you're passing something of that very, very derived tag type, it will call the one expecting the very, very derived type. And if you're doing something a little less derived, it'll have to call the one that takes the base tag type. Right, the first overload match is better because the required conversion to base class is fewer levels deep. Right, so this works great if you have this hierarchy that's already been made for you, like iterator category. Oh, yeah.
You have in the bottom function, shouldn't that be using iterator traits?
That bottom should be using iterator traits, but there wasn't enough room on the slide. But yes, traits classes, they appear everywhere. All right, so this works great if you have your iterator category imposed on you by the library, but what if you were the one making up the rules? Here's an example of me trying to make up the rules. Here, I make my own tag types. I have this in the header. I call it priority tag. Priority tag 0 is just an empty tag type, and priority tag 1 is just an empty tag type that happens to inherit from priority tag 0, and so on, all the way up, as many as I need, and I just make a template. And then, however many cases I have this priority tag. In this case, I have 2 cases, so I just have priority tag 1 and 0. And I dispatch. I go up here if I can. Right, I'm passing something of the most derived type, so I'm going to prefer this overload. But I'm going to prefer this overload only if it exists. And now, this is a template, and it's got this default argument, which may or may not be well-formed. I've taken the type trait is random access iterator v of it. That's going to be true or false in value space. I use enable if t to map that into SFINAE space. This default is now ill-formed or well-formed. If it is ill-formed, then this doesn't participate in overload resolution. And so priority tag 1 will have to be cast down to the base class, and I'll get this less specific implementation. However, if is random access iterator v of it is true, then this is well-formed, and of course then I will prefer it because it is fewer levels deep. And so I will do this. Now in this case, I'm just sort of duplicating. I'm really going back and forth between value space and SFINAE space because I'm duplicating work iterator category is done for you. This is more useful in cases where there's no hierarchy provided at all. I don't have this random access iterator tag business. In this case, I have allocator traits, even more traits, and still allocator related. And here's the implementation of allocator pointer, or allocator traits a : pointer. So allocator pointer t is going to be the decal type of what I get when I call the function allocator pointer of a, and I pass in the most derived priority tag. So I have 3 different functions allocator pointer of a, three different function template overloads here, taking different argument types. The most specific one, the one I would most like to pass this particular most derived object to, this would be a perfect match if it existed, but it exists only if its return type is well formed. So if a : pointer exists, awesome, I will use it. If it doesn't exist, then this one goes away. This allocator pointer overload goes away. Well, what's the next best match? That one didn't work out so well. Well, this one is pretty good. It's not that many levels of casting the base. It's just 1 level of casting the base. Oh, but it's only well-formed if A has a value type, and I can make a star of it. If the value type were a reference, that also wouldn't work. So maybe I can use that one. And if that doesn't work, well, then I guess I could just call allocate and get the type back from that. That's supposed to be a pointer, and I'll use that. So here I have things that may not be mutually exclusive. So I have imposed on them the ordering. I would like to use pointer if it exists, and then value type star after that, and then I would like to use the return type of allocate. And if I decided that I wanted to change those rules later, and maybe value type star is more important than pointer, for some reason. All I have to do is swap around these priority tag numbers. And I can add more cases. One place that I used a lot of this was in my dynamic cast from scratch talk. I didn't show that code, but that code is in the repo, where there are just so many of these different cases, and some of them take priority over others. And they're not all mutually exclusive. Of course, if you're in 17, this is good if you're in 14, as most of us, I think, are, or less. If you're in 17, you can use ifconstexpr, and you can just do something like this. And when you do that, I recommend write your own type traits, such as is random access iterator. Don't mess around with is base of random access iterator tag nonsense. Just write something that takes whatever question you're interested in value space, and just give it to me in type space. Give it to me in value space, and then I can ifconstexpr on it. But if you don't have this, if you don't have ifconstexpr, if you do have ifconstexpr, you can just list out the cases, right? If, else if, else if, else if, and it'll do the thing naturally. But if you don't have that, you can use priority tag to get the same approach. And I'm totally out of time. Thank you. Take questions.